Great. So for the second talk of the day, much anticipated as we got many emails after it was rescheduled. Our second speaker for the day is Professor Madeleine Udell. She is assistant professor in management science and engineering at Stanford. And she is also an associate professor with tenure on leave from Cornell. And she has been doing research on accelerating large-scale data analysis and optimization with a variety of applications and with a focus on exploiting problem structure to improve algorithmic approaches. She's received many awards, of them the Kavli Fellowship in 2023 and the Alfred P. Sloan Research Fellowship, as well as an NSF Career Award and an ONR Young Investigator Award. And today she's going to bring in large language models to this seminar for the first time, as is the case with every other seminar in every other field. So we're looking forward to that.
Okay, well, thank you for the lovely introduction. It's great to be here, and apologies to anyone who was there for the disappointing me not showing up for my own talk, which is the first time it's ever happened to me. So that happened in January, but here I am with even more interesting content for you, I hope. So I want to talk to you about AI and the future of optimization. These are sort of some initial explorations that we've made for how you can use large language models in order to improve sort of the scope of the kinds of problems and sort of the places where discrete optimizers like yourself can hope to sort of attack and improve all sorts of problems. And this is joint work with two of my students here at Stanford, Ali Ahmadi Tashnizi and Wenzi Gao. So what's the challenge, right? We know that optimization is really important across all sorts of sectors of the economy, right? And here I'm preaching to the choir, so I think I hardly need to say it, right? But optimization can improve efficiency and reduce waste almost everywhere. This is true in sort of smart grid applications. It's true in routing and logistics. It's true in scheduling, maybe for airline flights. It's true in supply chain. There are all sorts of problems, and the largest problems can afford to hire experts like yourself in order to, code up a solution to their problem and implement it in practice. But the smaller companies, or when sort of small things change or small problems at these big companies, they really can't afford to take the time to model the problem. And what's funny is that oftentimes the bottleneck really is modeling in applied optimization. It's not that you can't solve the problem. It's that it's sort of maybe not even worth someone's time to model the problem, or maybe they don't know how to model the problem. Maybe they can't get access to an OR expert who would know how to do it, right? So let me give an example of the kind of thing that I'm talking about, sort of the part of the optimization process that I'm focusing on here. So here's an example, which is a pricing problem that comes from the world's largest fashion retailer. So this is the kind of thing that you can imagine a domain expert, a business expert, a product manager or something at this company writing down. They could say, we sell articles of clothing, we've got lots of markets, we can estimate how price changes affect sales for each article. We've got to have the price changes being multiples of €1. We know initial prices, we're not willing to change more than 20% of the prices because that'll confuse the customers. Each article has a maximum production volume, and let's say we've got, given our sales forecasts, our past elasticities, our estimated elasticities, let's choose new prices for each article to maximize the expected revenue. Okay, so that's a sort of simple, straightforward problem. This is the kind of thing you can imagine a business expert saying. This is not the kind of thing you can imagine a business expert writing down, right? So this is Gurobi Pi code. So here we're modeling the problem in Python. And so you can see that many of the constraints from the previous slide are sort of expressed here, like quantity sold is less than or equal to sales forecast, right? So again, this is probably the kind of thing that's familiar to you guys, but a lot scarier to someone who doesn't have as much of an optimization background. So the question is, can we help people get from, this description to this that you can feed to a solver and provably solve, just give them the answer. Okay. Right. So solvers are extremely reliable, right? That part, I think, we all, it's the part that we know and love. But I think there's a lot more to do on modeling and trying to improve and make it easier for people to modularize out that part so that more people can use it. Okay. So how do we make optimization more accessible? Let's try to automate it. So what are approaches to automating optimization, the modeling phase of optimization? Some people have tried just asking the large language model for a solution. You can say, you know, large language model, here's my optimization problem, give them the business problem described before, maybe with some numbers involved, and you can just ask it to produce the numerical solution. Okay, so this is an approach that was tried in a NeurIPS competition sort of after the competition was 2022, and they discussed the strategy in 2023. It's also an approach that was proposed in LLMs as optimizers, which is a paper written by a group at Google Research led by Chengren Yang, who's actually a former PhD student from my group, where he proposed, you know, you ask the LLM for the answer, it gives you some value. You ask it in a slightly different way, it gives you another value. You ask it in a slightly different way, it gives you another value. And you could try to optimize the way that you ask it in order to optimize the value that it produces. So this is kind of an interesting approach to prompt optimization. You could ask the LLM to write a solver directly for you. So we've seen that in Fun Search. You could ask the LLM to call a solver. So you can ask the LLM to emit code that will call the solver. This is kind of like the approach that I sort of suggested earlier. And this was in concurrent work that was published at iClear. They call this chain of experts, where they have a bunch of different LLM experts collaborate to work on a problem. So there's sort of a sequence of prompts that are given to the large language model in order to improve the formulation of the problem. And then eventually you just take that, you run it as solver code. And then there's been a lot of work on chatbots for optimization. For example, you know, you give them an optimization formulation and you say, this is infeasible, help me fix the infeasibility. Or a group at Microsoft Research looked at doing what-if analysis. So they said, you know, what would happen if I eliminated this supplier? Or what would happen if my estimate of this price is off by a factor of 2? And asking the LLM to help explain what the optimization model would do or what it would mean. There's also been a modeling chatbot that was developed by Alibaba Cloud. Okay, so what are the big challenges in optimization modeling using large language models? I think the first one is long problem description. So you know, you guys probably know that the most complex realistic integer programming problems can be extremely long. So there was one that I found that was had a 60-page description for some energy systems problem. Like one table of parameters went on for 7 pages. This is a lot for a human to keep in mind and sort of model all at once. It's also hard for an LLM to keep all that in mind and model at once. And you're likely to see the LLM forgetting constraints. Okay, so that's a major problem. Big data matrices. So the fact that, you know, the largest problem is the one that we really care about, have huge data matrices. These may not fit in the context windows of LLMs. Okay, so it may be impossible for the large language models to sort of grok the entire problem at the same time. But it's also something that, you know, you should consider this to be a reason why you shouldn't expect the LLM just emitting a solution to be a good idea. Because, you know, large language models, how do they work? Essentially, they work by next word prediction. They look at the previous words, they predict the next one. They look at the sequence of previous words, they predict the next one. And this is something that works well when, you know, you've seen something that looks like this prefix, and so you can, you know, predict the next thing pretty well. But when it comes to large numerical matrices, you shouldn't expect them to have seen a matrix like this before, right? Your particular optimization problem, particularly as they get larger and larger, is probably unique. Okay, and especially if, you know, the operations required to solve the problem involve things like matrix inverses, there's just no way that you're going to get this by, you know, anything that looks like statistical learning. Okay, so it's really a case where you need to separate out the data from the problem description, have the LLM handle the problem description, and the data really should be left to the solver. Okay, so I guess what I'm doing is I'm justifying you know, all your guys' work. I think it's going to continue to be relevant no matter what happens with these large language models. Hallucination is a major problem. So oftentimes it'll come up with a constraint or a sort of a formulation that it thinks is just like more reasonable. It thinks it's, you know, its version is better than yours. Okay, so you have to be careful of this and make sure it's not coming up with constraints that sound reasonable but are not actually what you intended for your problem. And then bad models, right? I mean, the sort of classic thing that you guys worry about all the time is that some formulations are better than others. Some formulations are slower than others, right? How do you make sure it's, doing the best optimization it can? So how do you solve these problems, right? For long problem descriptions, I think the best approach is decomposition. So have it look at one constraint at a time, figure out how to separate the problem into constraints and have it just look at one thing at a time so it doesn't get overloaded, okay? There are, new large language models coming out with longer and longer context windows. So it's possible that it becomes irrelevant later, but it's not clear right now. To big data matrices, the solution is use a solver. To hallucination, I'd say the answer is testing. So if you can maybe even have the large language model write tests to check that each of the constraints hold, or to sort of, have multiple different large language models come up with multiple different, formulations of a single constraint. You can check that they're consistent. Okay. You could also check using a human when you're uncertain, right? So you'd need to be able to figure out when are you uncertain, when are the places where it's the sort of most important to call in a human. And for bad models, the solution, as it is for humans, is education. Okay, so we have to figure out how to educate the LLM in, for example, the best practices in mixed integer linear programming or whatever it is we're doing. Okay, the large language model can also introduce really subtle errors, like the code runs, but the result is incorrect. Maybe it ignores some constraints, or maybe a variable doesn't match a desired interpretation. So as an example, I've seen a case where it introduced a variable abs price, but there were no constraints that would enforce that abs price would actually be equal to the absolute value of the variable called price. Okay, you have to watch out for this kind of stuff, or more generally exploit the structure of optimization to reduce errors. So let me show you an architecture of a prototype system that we built called OptiMUS that tries to answer some of these challenges. Okay, so here's how it works. You have the problem description comes in. The problem description is sort of purely text. We do a little bit of pre-processing. Basically, this is sort of breaking it up into objective constraints and extracting the parameters to get an initial state. And we put the parameters here. So the actual numerical data is over here. The large language model doesn't see it. Okay. Now we go through and we've got a couple of agents. So think of each agent as basically a prompt. Okay, so it's a large language model and it has its own particular prompt, so it knows what kind of thing it's supposed to do. Okay, so the manager is in charge of deciding which worker to send the problem to next. The manager might send it first to the formulator. The formulator is in charge of taking all the natural language descriptions for each clause in the optimization and turning it into like a LaTeX formulation. Okay, the programmer is in charge of taking the LaTeX formulation and turning it into code, for example, the Gurobi Pi code that I showed you before. And the evaluator is in charge of running the code and interpreting the output, right? Either the solution or the error if an error was raised. So at the end of the day, the manager, he gets to decide, should I send it to the formulator again, the programmer again, the evaluator again, or do I think I'm done? Have I solved the problem? Okay. And when the manager decides the problem is solved, they emit the answer. Let's dig into this pre-processing because it's actually kind of interesting. So the preprocessor is also an LLM agent. It will go through the description and it'll decide which things in the description are parameters. So for example, it's decided that the machine time capacity, so it says while not exceeding resource capacities, it's decided the machine time capacity is one of the parameters, or the material requirement for each of each product for each raw material, that's another parameter. And it'll say, oh, the machine time capacity, that's a scalar. It depends on, this should be shape. It should say, M is a scalar. It's the number of different machine types. But the machine time capacity is a vector and it has M dimensions, okay? Or the material requirement is actually a matrix that's R by P, okay? The resources by products, okay? So it'll automatically figure out the dimensions of everything. And you can even do checks on these in order to make sure that the sizes of all your constraints make sense, okay? It extracts the objective. It extracts some background about the problem. This can help with sort of common sense constraints that might just come from common sense, but not be explicitly enumerated in the problem. And you've got you've got the list of constraints. Okay, so we try to take this description and then sort of pull out and enumerate the constraints. Okay. Now, once we've got that, say we send it to the formulator. The formulator is going to go through this list of constraints, right? We start with no variables. We don't know what the variables need to be in the optimization, but we'll go through the objective and each of the constraints in turn. And for each one, we're going to figure out which parameters it depends on and which variables it depends on. And if it depends on a variable that is not in our table of variables yet, then we add that variable to the table. Okay, so now we know which parameters and which variables each constraint depends on. That's great because it means that if we have to go back and fix something, we know exactly which which other elements in the problem we need to touch. Okay, so we could change something without changing the whole problem. We can just sort of edit pieces of the problem. Okay, so this helps with scaling. Okay, so let's see how it works. Okay, so now we're going to put on our computer science conference hat. Computer science conference hat, how does it work, right? You need to have a benchmark of problems. You need to have correct answers for all those problems. You need to have some baselines of, how other algorithms perform on that problem, and you need to show that your thing performs better than all the baselines on that benchmark, yeah? Okay, so let's try to do our computer science conference thing now. Okay, so here are the benchmark data sets for optimization modeling. The first one, NL for opt, comes out of this NeurIPS 2022 competition, which I think was kind of a prescient competition. They're pretty easy problems. They're all just linear programs. They don't have any integers in them. So this number in parens is the number of mixed integer problems. And they're relatively short. So the descriptions were only like 518 characters. Okay. Complex OR is a data set that was developed for this chain of experts paper published in iClear this year. Again, the problems are pretty short and there aren't very many of them. They do have 12 integer programs. We developed another data set, NLP for LP, which has longer descriptions, which we thought would be sort of also interesting and sort of relevant. And we doubled the number of MILPs compared to what was previously available. And we're continuing to develop sort of bigger, longer, harder data sets to push the limits of these methods. Okay, so here's the table, that shows our thing is better than everyone else's thing, right? So if you just ask ChatGPT to emit solver code and you try running that code, so you don't do anything clever, this is standard, you can solve about half of these easy problems, but you solve a pretty small fraction of the complex OR problems and a decently small fraction of our new data set. If you use, clever things like saying, think step by step, the solve rate goes up by a little bit, but really not by much. The chain of experts paper improves this to 64%, still only 38% on complex OR. And they get 53% on our data set. OptiMUS, which is the architecture that I showed you before, gets it up to almost 80% on NLP for opt, 60% here, 72% there. So it does beat the state of the art by a large margin. On the other hand, would you use this? Would you consider this reliable? Absolutely not, right? Absolutely not. Okay, so I would not suggest that, throwing the LLM at the problem, even in a sort of clever architecture like this, is enough yet, right? So let's dig into why it's not enough, what are the deficiencies, and let's think about how to improve, okay? Or the sort of possibilities for improvement, okay? So you can try OptiMUS with different LLMs as a backend. I think the main thing I want to point out here is that so here's the sort of baseline performances in this row. If you look down, if you replace the manager with GPT 3.5, the performance barely drops. But if you replace the individual contributors, so the formulator, the programmer, and the evaluator with GPT 3.5, which is a less powerful model than GPT-4, which is what we were using to run the other ones, the performance drops by a ton, okay, down to 28% or 9%. Okay, so it's just kind of cute. Dumbing down the manager is okay, but dumbing down the individual contributors is absolutely not. Okay, they need to be smart. Okay. Let's look at how many agent calls sort of OptiMUS is using. Okay, so for NL, for opt, basically you do perfectly well if you just call each agent once. So you call the formulator, the programmer, the evaluator, then you solve the problem, you're done, right? Allowing it to call sort of more agents doesn't really help. But on these harder data sets, allowing it to call more agents does help. Okay, so you improve the performance from like 0.45 all the way up to like, 0.7 something. On the other hand, Like, so there's some amount of, it learns from its errors. It notices errors and it fixes the errors. What kinds of errors is it fixing? We can see that a little bit better on this slide. Again, on the simple data set, which is NL for opt, among the problems that are correctly solved, generally, you formulate it once, you program it once, you evaluate it once, done. Okay. Among the harder problems, here's what generally happens. You formulate it, you program it, you evaluate it, you get an error, you go back, you program it again. So maybe you weren't using the function calls correctly. Maybe you forgot that you needed a list comprehension or something. Okay, so you program it again, you evaluate it again, you're done. Okay, that's the most typical trajectory. So in other words, it's very rarely fixing formulation errors. Okay, but when it fails, it's pretty evenly split between incorrect. There's some amount of incorrect modeling. There's some coding errors, and then there are still some missing constraints. Okay.
A quick question, Madeleine, if you don't mind. So here, when you say mistake, is it the optimal value of the model produced by the system is not the same as or the solution is not feasible in the true model, or what's the criterion for
what's the
correctness?
criterion for mistake? So we have a pretty strong criterion, which is that it has to produce the correct solution, right? We've created data sets so the problems have unique solutions, and we check whether it produces the same solution.
Okay, great, thank you.
Okay. So how can we imagine using a system like this rather than trying to solve the problem all in one shot? Using it to augment the abilities of a human decision maker. Okay. So here's an example. This is a production planning problem. Okay, so given number of products, you produce each one at a specific rate, certain number of hours in a week. A ton of each product has a known profit. You've got a lower and upper limit on production you can do. You want to maximize total profit. Total number of hours used by all products has to fit, within the capacity of the factory. How do you decide how many tons of each product to produce? Okay, so let's call our OptiMUS web app. Okay, so this is what it looks like. So I put in that description, and OptiMUS immediately goes through and it identifies what are the parameters. So it says, the number of products is P, hours available is the number of hours available in the week. We got a production rate for each product. Lower and upper limits. So it goes through, it identifies these parameters, and it does a quite good job, okay? And the dimension of these parameters. And if it left out one, you could add one here. If one of these was wrong, you could delete it there, okay? Now, you go through and you ask it to extract the objective and constraints. Here's the objective, here's the list of constraints that it finds. And if you look at this carefully, you'll see two constraints a little bit funny. One says the production volume for each product must be an integer value if products cannot be fractionally produced. Okay, that's actually just a tautology. It's not a constraint. Okay, so delete it, delete. Okay, next one, the production of each product is constrained by its respective production rate in tons per hour. Okay. That's not a constraint. That's actually the definition of a parameter. Okay, so you can delete that too. So this is interesting. We've seen two mistakes, but they're not like mistakes about understanding the problem. They're mistakes about like, what do we mean by a constraint? Okay, so this is kind of interesting. It means that it's something that you would expect could be improved by a strategy like retrieval augmented generation, which shows the LLM more examples of the kind of thing that you're looking for. That's a strategy that we're actively exploring right now. Okay, now let's go to the coding phase. So we say formulate all these things. So here's the natural language version of the objective and constraints, and it produces this LaTeX formulation. So let's look at the LaTeX formulations and make sure they're right. So here's one, non-negative production constraint for each product. And what do we see over here? We see tons sold is greater than or equal to the lower limit. Okay, that's not correct. That's not what we asked for. We asked for a non-negativity constraint. Okay, but it's actually not so bad. It's it's a true constraint. It's just not what we asked for. So again, it's a little funny. I would call this hallucination. Okay, now you upload your data, and the web app will actually create synthetic data for you if you don't have a data file that you care about. And it produces code. So you can run the code. When you run it, you get an error. Okay, so, and this is the thing, this is a wonderful button. You click fix code. Okay. And when you run it again, you get the run is successful, and it says you sell 3 tons of each of the products. Cool. So you can see how a system like this, it could speed up your modeling of a problem, even if you're someone who knows how to model optimization problems. On the other hand, it could easily lull you into a false sense of security, and it's sort of hard to notice when it's sort of hallucinated or done a sort of strange thing to a constraint. I think this is something that people are really struggling with AI, is how do you how do you use it without getting overconfident or lazy? Okay, I want to really briefly tell you about how we teach LLMs optimization, because I feel like it's super relevant to this group. Okay, so of course, a good optimizer exploits structure in order to generate models that can actually be solved quickly. Okay, so can an LLM do the same thing, right? For example, like we could sort of start to enumerate what are the kinds of techniques that people use in order to generate better models, right? Maybe things like exploiting special ordered set properties, indicator variables, noticing that, instead of sort of going all the way to the LP formulation, sort of using things like a norm or an absolute value and explicitly telling them to the solver. You could look for total unimodularity. You could notice if you've got a SAT problem or a constraint programming problem and call a specialized solver. Constraint generation, I think, is another. Constraint and column generation are really important techniques that I'd love to see incorporated at some point. So what we can do is we can ask the LLM, here's the problem description, like which of these techniques do you think might be useful? And then we can go through and ask it to reformulate the problem using these techniques. Okay, so here's an example. You can say, I've got an optimization problem. Here's the description. Here's the formulation. Now, there's this thing called total unimodularity. And here are the kinds of problems where it applies. Here's the definition. Does this problem satisfy total unimodularity? And if it does, please use that and improve the problem. Okay, improve the formulation. Okay, so you can try this, and it actually does work. Here's another example. This is a concrete problem where you say Stanford plans to build new dining halls on campus. There's a certain cost to build a dining hall of a certain capacity at each candidate location. You know where the students live, and your constraint is that there's no more than one dining hall that will be built in North Campus, and no more than one will be built on South Campus. Your goal is to minimize the distance from students to food, plus the building cost. Okay, so in this problem, there's one structure that I want you to really notice, which is that we've got this variable, which is the capacity at location K, which is 0 if it's not built. So generally, right, you'll have, among all the dining halls that could be built on North Campus, one of them will be non-zero and all the rest will be 0. Okay, so there's 2 reasonable ways of formulating this as a mixed integer linear program. One is to introduce binary variables for each location, right? And then say the sum of the binary variables on South Campus should be less than or equal to 1. The sum of the binary variables on North Campus should be less than or equal to 1. And then use a big M relaxation to say CK is less than or equal to some large number big M times XK. Okay, so that makes sure that one of the CKs is no more than one of the CKs can be non-zero among North Campus and among South Campus. Okay, there's another way you can tell this to Gurobi, right? So a solver, if it actually knows that you have this special ordered set structure, can take advantage and can actually use it inside the branch and bound, right? So you could say, actually, all these CKs are in a special ordered set of size 1. That means no more than one of them can be non-zero. So you're telling it directly. Okay, so here's what OptiMUS does. We'll try generating 2 codes. One uses the standard MILP relaxation, and that's sort of the default one that OptiMUS outputs. And the other is what OptiMUS produces when it's prompted to go back and consider this special ordered set technique and reformulate the problem if appropriate. So it does, and it reformulates it using this SOS concept in Gurobi Pi. And then you can see that as the number of locations grows, the SOS formulation is doing much better than the standard MILP formulation. Okay, so it is actually able to learn these advanced techniques if we can teach it, right? If we sort of remember, well, what are the techniques? What should it be looking for? Okay, so that's a wrap. I think the big question here is, what are the limits of LLMs for optimization? What are the things that it can do? What are the the problems or domains that we just haven't been brave enough to tackle it? We haven't had the tools to tackle, and now we can, right? What new problems does this open up for us as optimizers? Okay, so I've got a bunch of directions I'm super excited about. One is robust optimization. Sort of, I think a lot of people don't use robust optimization just because it's hard to think of the scenarios this. It's hard to think of what might go wrong or where your estimates might be wrong or sort of what to replace them with. And this kind of imaginative creation is something that these LLMs are very good at. So I think there's a lot of possibilities in robust optimization, synthesizing small data sets to check your models for correctness. I'd love to see, methods to automatically choose a solver or heuristic to meet your time or accuracy requirements. Of course, it's sort of straightforward to imagine extending this beyond mixed integer linear programming. And one thing that we're working on is sort of just improving the modeling, sort of getting it up to higher and higher accuracy, using tricks that are standard for large language models, in particular, retrieval augmented generation. So giving it examples of well-formulated problems, telling it that it might want to consider producing something similar. So I'm going to wrap there. I'm very happy to take your questions or ideas.
Great. Thank you very much, Professor Udell, for this very nice talk. So I think we can take one question now before breaking to breakout rooms where you can ask the speakers additional questions. So if there is any question now from the audience, we can take it. Maybe I see a raised hand from Minghao. Minghao, would you like to unmute and ask the question?
Yeah, so thanks, Madeleine. So I have a quick question, when you feed the large language model, I'm curious, you just describe the problem we see, in a typical formulation of the OR community language, or you just treat it as a non-professional people, I just tell you the demand or what I'm gonna do. Yeah, that's my question, because a lot of people will say, okay, I know the constraints, I know the objective, and that's a more readable way for the language model, I guess.
Yeah. So I think, this is interesting. You're bringing up the fact that, going from, we are much better able to write down problems, even in natural language, that will be easily translatable to a unique mathematical representation, and someone who's sort of an expert in the business and I might not be able to be. So I think sort of getting to that level and being able to handle the sort of very vague problems that someone might sort of initially formulate, that's very interesting. But I think it's a step. So I'm very excited to get to it, but we haven't gotten to it yet because I think we need to sort of deal with the easier problem first before we move on to the harder problem. So right now, these test sets that I'm showing you, basically the problems are basically what you would see in textbooks on LP modeling, or MILP modeling and formulation. We're starting to put in problems that we find in papers like in Inform's Journal on Applied Analytics. And then, we're hoping to move towards vague problems when we feel that the solve rate is good enough on these, more carefully articulated problems. But, it's hard to find what's the right test set for that, right? Where do you find these vague problems? So that's another, obstacle to overcome.
Thank you. Have you considered if you can human in the loop, the AI also can prompt the human to answer, to define the problem, to help them define the problem.
Yeah, exactly. So I'd love to see somewhere back and forth, right? The human says what they want, the AI says, maybe this is what you mean. Is that what you mean? Yeah, I think that's absolutely the way to do it. And so, in order to do that, you just need to make sure that you can sort of make an AI that's aware enough of when it's jumping to conclusions or making assumptions, so it can surface those to the human. So, that's definitely an important direction for future research here.
Okay, thank you so much.
Okay, great. So if there are additional questions for either Kim or Madeleine, please stick around. Alex will move us to 2 breakout rooms where you can chat more with the speakers. And thank you again, Kim and Madeleine, for both talks.
Yes, thank you. And join us for the next session on May 17th. Stay tuned for the announcement.